Hi there, and welcome to Raylene Math. In this video, we will take a look at rational functions, or a ratio of two polynomial functions. We do this so that we can start to understand discontinuities that happen when the denominator is equal to 0, and this is the basis for calculus so that it helps us to understand limits. So as we said, a rational function is a ratio of two polynomials, and we want to make sure that the polynomial in the denominator is not a constant, because if we have something like a quadratic polynomial divided by a constant polynomial, this is actually just a polynomial function because we can't have any zeros or any variable in the denominator. So let's first define domain, which is the set of x values that makes the function value or the y value defined. And when we talk about a value being defined, we really mean that the value is a real, single, or finite value. So to make the function value, remember that the function value is the output or the y value. And that's really the value that the function or the height of the graph is when x is a certain coordinate. And so to be defined, as we say in the next part, we want the number to be a real value, a single value, and a finite value. An undefined or not defined value either fails to be real or fails to be single, and then we call that indeterminate, or fails to be a finite value, and we call that infinite, either positive infinity or negative infinity. And of course, to be not real, we call that non-real. Okay, so in the first example, we have y is equal to 0 over 4, and when we solve the associated equation 4y equal to 0, there is one real single finite value for y that solves this equation. So the solution is defined. So this is defined, so the y value is defined to be 0 because there exists a real, or I should say a single real finite value for y in that equation. There exists a single real finite value, finite solution to that equation. In the next case, y is equal to 4 over 0 is the associated equation 0y equals 4, and this is undefined, and specifically the y value fails to be finite, so this is infinite. And infinite can be either positive infinity or negative infinity because y fails to be a finite solution in that equation. And in the last case, y equal to 0 over 0, we say that this is called indeterminate because in the associated equation 0y equal to 0, there exists more than one, so not just a single, more than one solution. And by solution we mean a real and finite solution to that equation. And so when y fails to be one single height on a graph, we say that the y value is indeterminate. And this is the equation that we're solving here is 0y equal to 0. You could substitute y equals 3, y equals negative 57, y equals 5,000,000.2, and all of those would satisfy this equation. In fact, there's an infinite number of solutions, but the infinite number of solutions doesn't mean that the solution is infinite. It means that there is more than one, or failing to be a single value. And so failing to be single, we refer to that as indeterminate. Let's acquaint ourselves now with some basic rational functions so that we can transform them to get more complicated rational functions that we will study in calculus. In number 3, the first basic rational function is y equal to x over x. And when we substitute x equal to 0, we get that the y coordinate is 0 over 0. This is indeterminate, and as we see when we look at the graph, we end up getting a graph that looks really simple. It looks like the graph of y equal to 1. The only difference is when we see the graph y equal to 1, there is no domain restriction. X is allowed to be anything, including x equal to 0. When x is equal to 0, the y coordinate is equal to 1. But if we take a look at the graph of x over x, which at first glance does look the same, and we have all of these same y coordinates and the same x coordinates, but if we take a look when x is equal to 0 in this graph, we see that y is not a number. In fact, y is trying to be an infinite number of possibilities because the y-coordinate is indeterminate. And so we can take a look, we'll continue looking at the graph for a minute, and we see that as x approaches 0 from the left-hand side, so as we come from the left side of the y-axis, the height is approaching, or the y-coordinate approaches a height of 1, and as x approaches the y-axis, or x equal to 0, from the right side, that y approaches a height of 1. It's just that when x is equal to 0, y does not equal to 1. We have a hole here. We're removing this point on the graph. So we'll fill in the table here. The limit as x approaches 0 from the left, the height that y is approaching when x approaches the y-axis from the left is a height of 1. Similarly, as we come from the right-hand side of the y-axis, as x approaches 0 from the right, and so we have x approaching 0 from the left written with a superscript, and we have x approaching 0 from the right with a positive superscript, either negative for left or positive for right. And on the graph we saw that y approaches a height of 1 when x approaches 0 coming from the right-hand side. Since these two right and left-hand heights are the same, but we don't have a function value defined, I'm going to put does not exist in this spot. We have a discontinuity, and the type of discontinuity is called a hole in the graph, and we can sketch the graph here using a different color to make it stand out. And we will emphasize the hole in the graph by removing the point at 0, 1. So for the most part, if we reduce this function, we would say that y is equal to 1 as long as x does not equal to 0. And so we would often simplify a rational function to a simpler function, removing that discontinuity, and then we would have to remove that hole, or remove that point, to make it look like the original function. The next graph, if we substitute y equal to x equal to 0, we still get y is 0 over 0, which is indeterminate. And if we take a look at the graph using technology, or if we were to make a table of values, we could start to see what's happening to the different y-coordinates for different x values. So if we just take a couple of x values, -2, -1, 0, 1, 2, and we plug those in, we can also make a graph at the same time. When x is -2, we get +2 over -2, which is -1. If we substitute -1, we also get -1 overall. If we substitute 0, we get 0 over 0, which does not exist. And so we have something weird happening on the graph, not a regular point to plot. When x is equal to 1, we get absolute value of 1 over 1, which is +1. And similarly, when x is equal to 2, we get the absolute value of 2, which is 2 over 2, which gives us a 1 overall. We really recognize that there's the absolute value or piecewise nature of this function, which is either negative the inside stuff when the stuff is less than 0, or positive times the inside stuff if the stuff inside the absolute value is non-zero. So to generalize, we might write that not with an x, but with an expression. That expression could be something like x squared minus 4, for example, inside the absolute value. And we can say the absolute value either changes the sign of stuff if the inside stuff was negative, or the absolute value does absolutely nothing and just removes itself if the inside stuff is non-negative, and non-negative means positive or 0. So going back to the graph of absolute value of x divided by x, that means that we are either going to get absolute value of x divided by x in each piece of the function, which is either going to give us a -1 height or a +1 height, and that's confirmed by our table of values. And so we end up getting a graph that looks like this. But when x is equal to 0, the y-coordinate is not defined. So let's consider the rest of the table. As x approaches 0 from the left-hand side, we see that the y-coordinate is approaching a height of -1. And as x approaches 0 from the right-hand side, remember that the y-axis is the line x equal to 0, and so coming from the right means that we are looking at values of x greater than 0. We see that y is approaching a height of +1. And since the height that y approaches from the left and the height that y approaches from the right are not the same, but they're finite numbers, we have a jump discontinuity. And we can sketch that graph here as a record of our basic function. And if you type it into technology, you can confirm that graph. Here we will take a look at the graph of y equals absolute x over x. And we can see that when x approaches 0 from the right, y is not a number. When x is 0, rather, y is not a number. But from looking at the graph, as x approaches 0 from the right, y does approach a height of 1. Similarly, as x approaches 0 from the left, y does approach a height, even though y doesn't equal the height when x equals 0. As x approaches 0 from the left, y approaches a height of -1. And it's interesting to note that the reciprocal of this function, which is x divided by the absolute value of x, is exactly the same graph. So whether we have the absolute x over x or the reciprocal, we have the same function. Okay, let's take a look at our next type of discontinuity. The next discontinuity is an example of a rational function. If we type, it's rational even though the constant is in the numerator, because we have to have a variable in the denominator. So when we substitute in 0 for x, we get that the y-coordinate is 1 over 0, which is infinite, and this value does not exist. If we take a look at the graph of the reciprocal function, y equal to 1 over x shows us that as x approaches 0 from the left-hand side, the y-coordinates are negative and approaching -infinity. Similarly, as y approaches 0 from the right-hand side, the y-coordinates are positive and getting bigger and bigger and bigger, approaching +infinity. So we can record that graph, and then in the graph, from the graph, we can write our information for the table. We often write vertical asymptotes as dashed lines. I didn't do that with my grid here, with my x and y axes. As x approaches 0 from the left, y approaches -infinity. As x approaches 0 from the right, y approaches +infinity. And here we have what's called a vertical asymptote. A vertical asymptote is just an indication that a finite x-coordinate is making the y-coordinate infinite. And I'm also going to specify that this has odd behavior because the function 1 over x is an odd function, and we see that approaching the vertical asymptote from different sides makes one +infinity and one -infinity value for the y-coordinate. Contrast this with the reciprocal square function, which is the 1 over x squared function. And here we have even symmetry and a vertical asymptote. As x approaches either 0 from the left or the right, y goes up to +infinity. So we know that substituting in 0 for x gives y equals 1 over 0, which is still, it doesn't exist, and the reason is because we have infinite, we have +infinity for both cases, and we have a vertical asymptote of even behavior. And our graph, we can just record it here. It's got slightly different points on the graph from the regular reciprocal. You would simply plug numbers into the table of values to get the exact coordinates, but we have the even symmetry, a reflection through the y-axis. Okay, the next thing we need to be comfortable with is converting our fractions between proper and improper form. So considering our rational functions are ratios or fractions of polynomials, we can consider first of all looking at number fractions before moving on to algebraic fractions. In the case of 2 and 1/3, this means 2 plus 1/3, and when we want to add fractions, we have to get a common denominator. So I'm going to multiply the 2 by 1 in the form of 3 over 3, and then add the 1/3. Now that I have a common denominator, we can go ahead and combine 2 times 3 plus 1. This has been learned as a trick as 3 times 2 plus 1 from here, but it's really because we're getting a common denominator. So we end up with 7 over 3. The 7 numerator is bigger than the 3 denominator, so this is improper. Whereas the fraction part we had before had a numerator or a remainder of 1. And so that was smaller than, purely smaller than the denominator, and the original mixed number 2 and 1/3 was a proper fraction. Working with algebra then, with expressions, we have 4x minus 5 over 1, and then we have the constant polynomial, if you will, of degree 0 of -3. To get a common denominator, we would multiply by 1 in the form of x plus 2 over itself for the first fraction, and then we would say x plus 2 times 4x minus 5, and then subtract 3 all over the LCD. And so we can use technology to check our answer for the algebra here. And I'm going to use the TI Inspire, and I'm going to get a common denom of 4x plus 5 minus 3 over x plus 2. Let's just confirm it was 4x plus 5 and not 4x minus 5. Yeah, it's 4x minus 5. Okay, so we'll put 4x minus 5, and notice that in the denominator I put that in brackets. So we get 4x squared plus 3x minus 13 all over x plus 2. So I'll just put that in here, 4x squared plus 3x minus 13, which is a quadratic or degree 2 polynomial over a linear or degree 1 polynomial. So we've gone from proper form into improper. Now we reverse the process to go from improper, where the degree of the polynomial or size of the number is the same or greater than in the top than in the bottom. We're going to convert it to proper. So in the case of 5 dividing into 99, we perform long division, and we see that 5 goes in 19 with a remainder of 4 number of times. And so that remainder of 4 really becomes the numerator out of the fraction part. So we get 19 plus 4/5, or 19 and 4/5. So we do the same kind of long division, or if we have a linear denominator, we can do synthetic division. Here I'm going to use the prop frac feature on the calculator to do that step for us. So you can do it by hand and convert and compare your answer with the calculator. So we have prop frac for the x cubed plus 2x minus 7. Let's just confirm. Plus 2x minus 7 divided by the denominator, which was 2x plus 1. And so we get a quotient part, the part that has a denominator of 1, of x cubed plus 2x, and we get a remainder, the numerator of this fraction part, of negative 7. And so we can write that in as a proper fraction, because we have a degree polynomial 0 over degree of the polynomial 1. So this is definitely proper. So writing that in, we get x cubed plus 2x as the quotient, and then the remainder technically is the negative 7, but we often put the negative here, multiplied by positive 1, and that's divided by 2x plus 1. So there's the conversion back and forth and relating proper and improper fractions between the algebra and the numerical examples. Some other features that we need to be clear on rational functions, just like any function, is the intercept. X-intercepts and y-intercepts. So an x-intercept is a value of x that makes the y-coordinate equal to 0. And because when we're dealing with functions, we can have more than one x-intercept because we're finding that the different x-intercepts correspond to one output, and we can have multiple intercepts. More than one x value can correspond to one output on a function, so we can have multiple x-intercepts. Meanwhile, when we are looking for a y-intercept, there is only one intersection of a function with a vertical line, such as x equal to 0. And therefore, by the definition that a y-intercept is a value for y that makes x equal to 0, we are looking for an intersection with the blue graph with the red vertical line, x equal to 0, and there can be only one y-intercept because there can be only one function for the x input of x equal to 0. One y value, one function value. Only one y-intercept, one function value corresponding to x equal to 0, one input. Okay, we've got a couple of discontinuities, and in rational functions they primarily come from the denominator being set equal to 0, and we saw that if the denominator is equal to 0, we could have non-zero over 0, which leads to the y-coordinate being infinite, and positive or negative infinity for the y-coordinates means that we have a vertical asymptote of the graph. The other possibility of having 0 in the denominator is if the 0 is also in the numerator, and this leads to either y being indeterminate, which we saw can lead to a hole in the graph, like the graph of y equals x over x, or it could lead to a jump in the graph, like the parent piecewise function absolute value of x over x. And so those are the different possibilities we have for the discontinuities of rational functions. So we're going to consider these basic graphs in more complicated ways in the next video, looking at some examples. When we consider some of the details of holes in the graph, you can read through here, take a screen snapshot of this if you want as we go through examples in the next video. But here we have some description about holes, some description about jumps, and some description about vertical asymptotes. One thing that is true about a vertical asymptote is that they cannot be crossed or touched by the function value. The reason for that is a vertical asymptote is characterized by y being or approaching positive infinity or negative infinity, and y can't ever equal positive or negative infinity, which means that the graph of y equals f of x cannot be intersected with plus or minus infinity for y, and therefore no intersection means no touching or crossing. Contrasting with that, though, we talk about the end behavior. And in the case of end behavior, we want to talk about the zoomed out behavior of a graph. We can take a look at a simpler case of zoomed out behavior that doesn't have anything to do with rational functions. If we take a look at the function 1 minus 3x minus x squared, we can see that this graph is going to be a concave down parabola, and what we're really doing is looking at the leading term of this polynomial. These two graphs are not the same, but when we zoom out far enough, they eventually start to look the same. And so we can say that when the values of x get really big in positive values or negative values, that the lower order terms contribute less numerically to the calculation of the output function value. And so we can say that the purple y is approximated by the red y value, or by the red y formula. This is really what we say when we have an end behavior or a zoomed out behavior or a non-vertical asymptote. A non-vertical asymptote is when the shape of the graph, when the graph makes the y-coordinates approach positive or negative infinity. So the opposite of a vertical asymptote, a non-vertical asymptote, must be when x approaches plus or minus infinity. And when x approaches plus or minus infinity, you can see that the x-coordinates are getting bigger on the right or bigger on the left. So that happens when we zoom out or when we look at the end behavior. So if we take a look at a simpler graph, if we have y equals x cubed minus 1 divided by 2x minus 5, for example, we know that this is a more complicated function that will take some analyzing sign charts and factoring and so on, looking at proper form and getting different pieces of the graph. But if we want to look at it in a simpler form, we can simply see a ratio of the leading term of the top divided by the leading term of the bottom. And in this case, this function simplifies to y equals 1/2 x squared. Now we know what the graph of 1/2 x squared looks like. And it's the same as the red graph, so if I turn off the red, you will see blue. But it's not the same as the purple graph. The purple graph, for example, has a vertical asymptote at the x-coordinate of 5/2. That means that when x approaches 5/2, the purple y-coordinate approaches either positive infinity or negative infinity. We can see that vertical asymptote there very faintly in gray. But the blue graph doesn't have any discontinuities. So these two graphs clearly are not the same. They don't overlap at all, not like the red one and the blue one. But when we zoom out, we can see that the purple graph and the blue graph start to look the same. And if we take a look at a special range, let's take a look from, let's say, negative 50 for x to positive 50, and let's go from negative 100 to positive 100. In fact, let's make it 1,000 for the y-coordinates. We can see that those two graphs are really starting to look alike. And it doesn't really matter what was happening around x equal to 5/2, because when we zoom out, we're considering a different set of x values. So we're really considering a different behavior. And so in this way, the purple graph behaves much like the red graph, which is the same as the blue graph. So when we are talking about zooming out or letting x approach positive infinity or negative infinity, we're really interested in the leading term of the top divided by the leading term of the bottom, which then becomes a much simpler parent graph from polynomials that we can analyze. So what we're going to do is take a look at this end behavior as a zoomed out behavior, which is a type of asymptote, but it's not the same as the vertical asymptote. In particular, it's important to note that we may have a function crossing or touching the end behavior asymptote. This is not the case for vertical asymptotes. Okay, moving on, we're going to take a look at some sign charts in the next example when we see these actual graphs. We're going to do some exercises, and the sign charts are really going to help us here to come up with where the graph lies above or below the x-axis on certain intervals. Okay, Well, we'll actually take a look at these exercises now. We'll just continue on from here. So we're going to consider all of these 7 steps or 8 steps here. These 8 steps characterize all of the information in the handout and the video information above, and we're just going to start applying it. So the first function we will take a look at is x cubed over x plus 1. And we're going to follow these steps. So example 1, we want to come up with the graph of f of x is equal to x cubed over x plus 1. And the first thing we're going to do is put the function in factored or reduced form. There's no factoring or reducing to do here, so we see that we don't have any common factors. It's not like we have, for example, x plus 2 times x cubed over x plus 2 times x plus 1. And so we don't have the possibility of a y value being equal to 0 over 0 for a certain x value. And since we don't have a graph that looks like x over x or x plus 2 over x plus 2, we're not going to have a hole in the graph coming from that parent graph we saw earlier. So this tells us that, rather that's the wrong graph, that's the jump discontinuity graph. This is the whole graph that looks like x over x. The graph of x plus 2 over x plus 2 would simply be a translation 2 spaces to the left using our basic transformations from pre-calculus. So what I'm saying is we don't have this common factor, so we don't have to consider a hole in the graph. So let's go back and take a look at just the blue function. And in this blue function we have some numerator and denominator, and we're going to start to analyze those according to steps 2 through 7. So here, step 2 says to get the equations of the vertical asymptotes. And so we are just going to list that we have none for holes. And for vertical asymptote, once we are working with the reduced function, there should be no common factor. So we're going to set the denominator only equal to 0, which tells us that x is equal to -1. What this is really saying is if we were to substitute -1 for x into the original function, we would get -1 cubed over 0, which is infinite. And that infinite is either positive infinity or negative infinity for the y-coordinate, depending on the sign chart. But what it's really saying is that we have a vertical asymptote at x equal to -1. The next thing we want to consider are the x-intercepts. And the x-intercepts, recall, are values for x that make y equal to 0. Now, if we have a fraction and we have 0 over 0, this is indeterminate. Meanwhile, non-zero over 0 is infinite, which is either positive or negative infinity. The only way for the y-coordinate to be equal to 0 is if we have 0 over non-zero, and then that value is defined to be 0. So we are specifically taking the numerator, once we have the reduced fraction and no common factors, and setting the numerator only equal to 0. And so x cubed equal to 0 says that we have an x-intercept at x equal to 0. It's a triple root, so it's going to have a behavior like a cubic function. It's going to flatten out at the x-intercept. Now once we have these pieces of information from steps 2 and 3, the vertical asymptote and the x-intercept, we are prepared to make our sign chart. So for our sign chart here, we are going to plot the x-intercept number of 0, and we know that that's a value of x in the domain, so we're going to use a solid line as a boundary for that. Meanwhile, x equal to -1 is not allowed in the domain. It causes a type of discontinuity, so we use a dashed vertical line. Then we put all of the factors from the reduced function. Now in this case, the reduced function is the same as the original function because we didn't have any common factors. And that told us that we didn't have any holes or jumps in this graph. So we're going to then list all of our factors along the side. I like listing my factors in the order that the x-coordinate of the vertical asymptote or the x-intercept showed up. So the factor that gave us the root of -1 is x plus 1. And the factor that gave us x equal to 0 came from x cubed. It's important to include the exponents on this so that we get the correct signs when we fill in. Now we could fill in the sign chart as a table, and we can fill that table in numerically by taking from region 1, region 2, and region 3 a test x-coordinate. So we could choose x equal to -2, x equal to -1.5, and x equal to 0.8, for example, if we wanted. And then we could take those x coordinates and plug them in for x into each of these 6 spaces in the table above. If we do that, we're going to get negative, positive, positive. It could be -1, or if we chose a different x coordinate here, like -10, then we would get -9. The point is, no matter what x coordinate we choose in the first region, the first factor will give us a negative value. If we take the same x coordinates and plug them into the x cubed row, we would still get negative, and then we would get negative in the middle region, and then we would get positive. I would like to consider thinking graphically when we are filling in the sign chart, and so the graph of the line y equals x plus 1 is a line that passes through an x-intercept of -1, and it increases. And so we can see to the left of this x equal to -1 line, all of the y coordinates are negative, and so we will record a negative in that spot. Then, after that x-intercept, or x value of -1, which is the 0 of the factor we're dealing with, all of the y coordinates are positive. And in filling in the sign chart this way, we can work much faster than if we have to slow down and plug in the numbers into formulas or expressions to calculate. So I'm going to consider how do we do the second factor's sign chart working graphically as well. Well, the graph that we're considering in the second case is y equals x cubed. And the graph of y equals x cubed has an x-intercept of 0, has a horizontal tangent, and is always increasing like this. And so to the left of the x root for this factor, we see that all of the y coordinates are negative. And so we record negative in the sign chart to the left of x equal to 0. Remember, x equal to 0 is the root of the x cubed factor. And then to the right of that x-intercept or root, all of the y coordinates are positive. And so in this way, we think graphically and we fill in the sign chart, which is a numerical type of expression of the sign chart. And so once we have that sign chart of 6 signs filled in, we can then consider what happens if we take the x cubed and divide it by the x plus 1, and we get the sign for the y coordinate that we're interested in. And the y coordinate signs will depend on, are we in region 1, 2, or 3. So negative divided by negative gives us positive, negative divided by positive gives us negative, and positive divided by positive gives us positive. I like filling in a sign chart in this way because then I can extend my sign chart to making it the Cartesian plane, and I can get the xy plane and produce the graph. What I like to do with this sign chart then is to shade where the y coordinates are positive or negative, where the graph won't lie. In region 1, the f of x, or the y coordinate, is positive, which means the graph will lie above the x-axis, because that's where y coordinates are positive. Therefore, the graph of this f of x will not lie below, and so I'm going to shade that so I'm not trying to draw any graph in this region. In the middle region, when x is between -1 and 0, the y coordinates by the sign chart are negative, and as a result, the graph is going to lie below the x-axis and therefore not lie above the x-axis. In the third and final region, the y coordinates are positive, so the graph of f of x lies above the x-axis and not below the x-axis. Right away, I have eliminated 50% of the real estate of this plane, and I know where the graph should be drawn. So we've done step 4, and we're going to continue with the remaining 4 steps. Once we've done the sign chart, we've really swapped from the x-coordinates, and now we're turning to our attention towards the y-coordinates. So in step 5, you'll notice that we are getting the y-intercept, and the y-intercept is the value of y that makes x equal to 0. So we substitute x equal to 0 into the reduced function. We're going to work everywhere after step 1, after getting the hole in the graph. We're going to work with the reduced function, because the only difference between the reduced function and the original function is a common factor, which leads to a jump or a hole. So once we've identified that hole, let's say, then we can work with a simplified reduced function to get all of the other information about the graph. And so now we see that the x-coordinate of 0 gives us 0 over 1, which is defined to be 0. 0 over non-zero is 0, unlike any other combination of 0 in the fraction. And so we can start to plot that information. I'm going to I'll draw my graph in red so it stands out. I'm also going to erase a lot of the sign chart information that I didn't need that's in my way. I think that'll do. And we can go on to step 6. Step 6 says to get the equation or the type of the end behavior asymptote. What that really means is to come up with the quotient. One, we put the improper fraction into proper fraction form. Remember that a numerator divided by a denominator is equal to the quotient plus the remainder over the denominator by something called the division algorithm. And we practiced that a little bit earlier in the video. So we need to come up with the quotient, so we're going to do long division. Now, on one hand, we're talking about zooming out, and the function of y equal to x cubed over x plus 1 is going to have the same kind of zoomed out behavior as a simpler function, and that's the function with a monomial in the top and a monomial in the bottom. The monomials, or the leading terms that dominate for big x values. And when x gets really, really big, the term x dominates the value of that denominator much more than the quantity of 1. And so this is a simpler expression to work with, and we see that y equals x squared for the zoomed out behavior. And that's more or less the same of this. Let's see what happens when we do the long division of x cubed over x plus 1. And so we're going to do this again by prop frac, putting our improper fraction into proper fraction form. You should be able to do this by hand using long or synthetic division. So we end up getting a quotient which is x squared minus x plus 1 and a remainder of negative 1. And so we're going to write that here, that the blue graph is equal to x squared minus x plus 1 and then plus a remainder of negative 1 over the denominator x plus 1. What we're finding though, as x gets really, really large in the positive or negative directions, as the magnitude of x increases, this term approaches 0, and these terms, well, they don't approach 0, but they don't get nearly as big or as important as the leading term. Okay, now the next thing we need to do is to see if the function f of x in blue crosses the green quadratic end behavior asymptote. So we're going to do this by looking for an intersection point between two functions. And so the intersection point is going to be between f of x, or y equal to x cubed over x plus 1, and the green end behavior quadratic parabolic asymptote that we found. Now I'm going to take advantage of the proper fraction form that we expressed the original function in order to solve for any intersection points, because when we solve for an intersection point, while a lot of people say set them equal to each other, what we're really doing is eliminating or substituting. So I'm going to substitute x squared minus x plus 1 from the green equation 2 into y from the blue equation 1. And writing the proper fraction version of this function, the blue function, we can simplify much more easily because we see the first three terms on the left and on the right are the same. And so we simplify this equation to say that 0 is equal to negative 1 over x plus 1. Now recall where this came from. It really came from, the negative 1 came from the remainder, and the x plus 1 is the denominator from the proper fraction form. And so solving this simplified equation, if we clear the fraction by multiplying by the denominator, we're saying that the remainder is equal to 0. And so if we multiply both sides of this equation by x plus 1, we get a statement that says 0 is equal to negative 1, which is false. And this tells us that we do not have any intersection points between the blue function and the green non-vertical or parabolic asymptote. And so in other words, f of x does not cross or intersect or touch the end behavior asymptote, or the non-vertical asymptote, or the parabolic asymptote, or quadratic, whatever you want to call it. And so in step 8, we're going to take all of this information, put it together, and come up with a fairly accurate sketch of the graph. So we're going to plot all points, holes, asymptotes. We've plotted the x-intercept, which is the same as the y-intercept, and it's there in red. And then we're going to plot the vertical asymptote is there in blue, x equal to negative 1, and we're going to plot the parabolic asymptote, which is y equals x squared minus x plus 1. And we're going to have a vertex somewhere over here at 1/2, 1/2, and get a parabolic asymptote that looks kind of like this. And we will extend it on the other side. And I'll also extend my vertical asymptote. And I said I would sketch the blue graph in red, but I'm going to sketch it in blue because it's the same color as the equation. We have some other information. We know that as x approaches -1 from the right, that y goes down towards -infinity. When x equals 0, y is equal to 0, so we have this piece of the graph. As x approaches positive infinity, we know that the blue graph is going to look like the zoomed out end behavior dashed green parabola. And we also know that the blue graph doesn't cross the non-vertical asymptote. So we're going to have something like this. And as x approaches -1 from the left, y approaches positive infinity. And so we're going to have a graph like this. And as x approaches -infinity, y has to take on the shape of the green parabola without crossing it. And so we know that the left-hand branch of the vertical asymptote is going to be contained inside of this little region. And there you have it. That's the graph of y equals x cubed over x plus 1. Let's take a look just once more at our graphing program, and we can see how our graph looks compared to this one. We've got a branch of the blue graph on the left-hand side and on the right-hand side of the vertical asymptote, and I think we've done a pretty decent job. So there you have it. These 8 steps are going to do a decent job until we get into calculus and finding max-min points, intervals of increase, decrease, concavity, and inflection points. It pretty much comes up with a reasonable shape of the graph as pre-calculusly as possible. I'll make another video for part B as an example and part C, because this video is getting a little bit long. So thanks for checking out Raylene Math.